Okay, so for at least the most of today, I'm going to go through the example we did yesterday that you worked on. And then I'm going to show how you can use a simplification based on the fact that two of those four members in that problem are two force members. And then I'll show sort of an extension of that two force members thing, which is the truss simplification. Before I go into that, a few people have asked me, have come to me and said, they're not doing as well in the class as they would like, and they want to know if I have any advice. And if you're already, so this is my advice, and if you're already doing this, I'd be happy to talk, and you're not happy with how things are going, I'd be happy to talk to you more about it. But this is my, like my expectation of what you're going to do with the problems and the lectures and everything. I'm doing this class thinking that what you're going to do with this material is you are going to not just take notes and watch the lecture, but you're going to read those notes all the way through multiple times. You're going to try to remember what I said the same way you would in like a biology class or something. It's not very much material, so I don't feel too bad about expecting that. I've tried to cut down on the amount of stuff that you need to remember by not having a textbook, so you don't have like 200 pages to wade through or whatever. It's just a small amount of handwritten stuff. But so that's my first recommendation is you need to remember all that stuff. It's not, so that's my intention, first of all, with the notes. And then the second thing is these problems, the problems on the exam are very similar to them. And so I don't think you should think of those. I only collect these problems once. But I think every bit of time you spend redoing those problems and doing them real consciously, like thinking, okay, not just like it's easy to, if you redo a problem, especially more than twice. So say you're doing it a third time, it's likely you're going to remember some of the numbers or whatever. But if you just remind yourself, like, why am I doing this? Why is this negative? Why does this go here? Think about, like, how would you explain the method to somebody who needs help with this class? If you can get to that point with all of these problems, then I think the exams should go really well. Obviously, the quizzes will go well, So that's my first bit of advice, my first iteration of advice for anybody who is disappointed with how the class is going. Do that first, and if that doesn't work, I'd be happy to talk to you about other stuff. But if you're not doing that, then that's what you need to do, okay? All right, so yesterday we did this thing. We had this cantilever beam. And it was connected by a roller to a member like that. And then pin joints connected a third member. And then there was a fourth member like this. And we neglected the weight. And if this was the problem, who can tell me what the external loads would be? Zero. Yeah, very good. So you need to have some kind of external load, and that's the 5,000. This angle is 30 degrees. The length is 2 meters. This height is 1 meter. And I numbered it 1, 2, 3, 4, and let's represent the joints as letters, so A, B, C, D, E. And we put the coordinate system there, is that right? Oh, at D.
Yeah.
Okay, so I'm going to do the free body diagrams, and then I'm just going to give you the answers and show what those look like as external loads. Save all the trouble of going through all the equations. But in a problem like this, I think the trickiest part, the place where you're most likely to make mistakes is getting the free body diagrams right. Okay, so free body diagram of 1. You have a fixed joint at E, so there's a reaction force, I'll call that RE, and then a couple ME. The next place that there's contact with the outside boundary is at D, and at D, member 4 is pushing down, so we have a force like this. I'll just call that N. That's our only normal force. And then at A, the pin is part of member 1 because it's the lowest numbered member. Am I going to draw that? Anybody want me to draw that? No? You don't even want me to do what I'm already doing? Okay, so that means that since the pin is part of member 1, we have a force on 1 by 2 and a force on 1 by 3. Okay, so that's it for member 1. Then member 2. The pin is not part of member 2, so at joint A, the only thing touching member 2 is the pin, which is also known as member 1. So we have negative force on 1 by 2. And then up at B, we have the force on 2 by 4. And then at B, member 2 is the lowest numbered member. So that 5,000 Newton force is being applied to member 2. So we also have the 5,000. A few people yesterday put that 5,000 on member 4 because it looks like it's applied directly to it. That'll work perfectly fine. This thing about grouping the joint with the lowest numbered member is just a system so you don't double count forces. Okay, so if it looks like it's part of member 4, it may seem surprising. All your free body diagrams will look different, but in the end, when you plug those forces back into your free body diagrams to figure out all the external loads, they'll all be exactly the same. Then free body diagram of member 3. Down here there's the force on 3 by 1, so that's negative F13. And over here there's the force on 3 by 4. And that's it. And then the last one, free body diagram of member 4. The pin is not part of member 4, so that 5,000 isn't acting on 4. The pin is touching member 4, so that's the force on 4 by 2, because the pin is part of 2. So that's negative F24. at C, you have the force on 4 by 3, which is negative F3, 4. And then at the roller, member 1 is pushing up on the member, so we have N. The list of variables, we have F12, that's a vector, F13, I'll do all the vectors first, RE, F24, F34, and then the scalars are ME and N. Did I miss anything? What did I miss? 1, 2, 1, 3. I don't have anything written as T here. So 2, 4, 6, 8, 10, 11, 12. So yeah, that's 12 variables. And equations, we're going to get 3 here, 6, 9, 12. So 12 and 12, and you can solve it. And if you solve it, you get F12 is equal to 4330, 4330. F13 is 0, 0. That's a surprise. F24 is equal to 0, 6830. F34 is 0, 0. RE is negative 4330, positive 2500. ME is positive 1830, and N is 6830. Okay, so let's take one more step. Okay, so the first thing you can eyeball here, you get done with something like this. It's very hard to have intuition about what these loads between members in a complicated structure are going to be. But you know that if you have any pushing contacts, any normal forces, rollers, or frictionless contacts, those scalar values that represent it need to be positive. So this N is one of those, and that needs to be positive, and it is, so that's a good sign. Now the next thing that we know is we have two two-force bodies. Body 2 and body 3 have no couples, and the only forces they have acting are one at each of the two joints. It doesn't look like it immediately for body 2 because up at that joint, whatever I called it, B, you have a force vector F24 and a 5,000 Newton force, but those are acting at the same point, so that's really just one force vector. So you have one force vector here and one here. And what you know is two force bodies, if they're in equilibrium, those forces have to be equal and opposite, and they have to be parallel to the line between the two forces, where the two forces are applied. So we can plug these in and check that. So let's plug these back into the free body diagram for member 2. So member 2 has F24, which is so 0, 68, 30. And then it also has that 5,000 Newton force that's at an angle of negative 30 degrees. So that's plus 4330, negative 2,500. And down at the joint A, body 2 has the negative of F12 acting on it. So this is negative 4330, negative 4330. Yeah. How's it going? You want to lecture for a while?
Oh, I'll sit and take notes for the first day and then
Okay.
see where I'm at.
Okay, so add these up. At joint B, you have 4330. Subtract this and you get 4330. Down here you get the negatives. This is at an angle of 45 degrees, and if you do the trigonometry, this does exactly what we think it should do. You have a force going this way. Can someone calculate the magnitude of that? 4330 squared times 2 square root. $61.24. $61.24 there. Okay. Anybody have any questions about that? So that's a strong suggestion that things are going right. It's very unlikely that you would get random numbers to be exactly parallel to the line between those two joints. Okay. And now let's go to member 3. So member 3, we have F34. Oh, well, this is going to be boring. We have 0, 0 up here. We better have 0, 0 on the other side. Yep.
How did we get the 6124?
That's the magnitude of that vector. So if you take the square root of the sum of the squares of that vector, this is what you get. Member 3, okay, negative F13, and you get 0, 0 on the other side too. Okay, well that's sort of, that's not quite as satisfying as the other one.
No.
I guess 0, 0 is parallel to the line, but
Not like, oh, it works.
yeah, right. Okay, but anyways, neither of those two violate what we expect to happen with a two-force member, so that's a good sign. We could also do this problem using the assumption that those are two-force members to begin with. So let's see how we would do that. So this is the two-force member simplification. This is the basis of the approach, the special approach for trusses. And so that's probably the most important reason that this is worth hearing about. So this is what the truss simplification is based on. So if you have any two-force body has two possibilities. It could be in tension, where you have a force that way and a force this way. Or it could be in compression, where the forces are both toward the center of the body. There are no other possibilities. The one that we just calculated, member 2, was in tension, because those forces are doing like what cables would do on the end. So what we're going to do, so if you know something's a two-force body, assume it's in tension. So you just assume that you have this case. And if it happens to be compression instead, when you calculate this variable f, you just get a negative value and it works perfectly fine. So, in other words, we just act like these two force members are cables. Mathematically, we just treat them like they're cables. The only difference is at the end you could have a positive or a negative value for it. So treat two force members like cables, where the tension can be positive or negative. Okay, so let's see how this works. At any joint connected to a two-force member, isolate the pin, or isolate the joint, and treat it as a particle. Remember, when we did our first structure, that's how we did it. We treated all the pins like particles. It increased the number of variables a little bit, so we started lumping the pins in with bodies. But now, whenever a two-force member is connected to a pin, we're going to isolate it. Okay, so let's see what these free body diagrams look like. So first, we'll isolate the two members that aren't two force members. In this problem, that's 1 and 4. So free body diagram of member 1. At the wall, we have a reaction, RE, and a couple, ME. At the midpoint, we still have that normal force. But now we have to treat A differently, because A is connected to actually two different two-force bodies. Okay, so over here now, we have the force on member 1 by the pin A. Okay, we're not lumping the pin in with member 1 anymore. So the force that's applied to member 1 at this joint is the force applied by the pin. Okay, that's not an internal force anymore. Okay, ask me questions about that. Or express rage or something. Show some emotion.
Could you that one more time.
Okay. So the two joints that at any joint connected to a two-force member, we're going to isolate that joint. We're not going to lump that joint in with the lowest numbered member.
Okay.
Okay. And okay.
So what if you have two forces acting the same point on one end and the other end you only have one? Is that still two force because there's only still two directions acting the same point?
Say it again.
So, like when we had a couple connected, for some ends we might have like two forces, but they're still acting on the same point.
Yeah,
in the same direction.
that's right.
But then we have another one that's acting opposite. Are those two forces and this one force still considered a two force?
Yes, because any forces that act at the same point, you can lump them together, and it's a single force vector. Yep. Okay, so in this example, the joints that we have to isolate are A and B, because those are the two pins that are connected to two force members. Okay, so using that full approach, we treated A like it was part of member 1 and B like it was part of member 2. But now we're not going to do that because those are connected to two force members. So we're going to isolate A and B on their own. And that means that, so look at now if we look at a side view of what's happening, a side view at A, let's see, we have member 1, member 2, and member 3, and then a pin connecting them. So I'll call this pin A. Our usual approach is we lump this pin in with member 1 because it's the lowest numbered member. And then 2 and 3 are both acting on member 1. But now A is not part of member 1. It's its own thing. So what's in contact with member 1 now? The only thing in contact with member 1 is that pin A. The only thing in contact with 2 is that pin A. 3 is that pin A. Okay, and that's why the only force at A on member 1 is F1A. And then the free body diagram for 4. We have the normal force. I missed one of these. There's in the so if we're going to isolate all the joints that are connected to two force members, we need to do C too. All right, so member 4, at B, there's the force on 4 by the pin B. And at C, there's the force on 4 by the pin C. And now we're going to isolate the joints. So pin A. What forces are acting on A? So I drew a picture here. 1 is touching it, and Newton's third law says that this force applied to A by 1 is negative F1A. And now we're going to use that two-force member simplification. The other two forces, we're treating member 2 and member 3 like they're cables, right? Because we know the direction of those forces. So we have one force here that I'll call F2, and one force here called F3. And we know the directions of those. We can figure out the unit vectors for those. Any questions about that one? Comments?
Where are those F2 and 3 coming from again?
Those are, so remember that all the two force bodies we're treating like cables. And so, I mean, I could have written these as T's, but they're not.
Okay.
So those are like the tensions applied by member 2 and member 3. Yep, right. And when we go to B, what forces do we have acting at B? We have the force applied to B by 4. Okay, so that is negative F4B. And then we have this force, F2. That has to be the same as this F2. And we have the 5,000 Newton force. And then the last one, the free body diagram at C. We have the force vector on C by 4. That's negative F4C. And then we have the force in the known direction, F3. Okay, so how many variables do we have? We have F1A, RE, N and ME. And then the free body diagram of 4, we have F4B and F4C. And then from pin A, we have F2 and F3, and I think those are the last two variables.
Are you saying since you do that free body diagram 4, that one's a 2 force member?
Which one?
The free body diagram 4?
No. This one has these 3 points where forces are applied.
Even though they're in the same like line, I guess line back.
Yeah, right. Well,
There's 2 forces acting on that line. Well, there's 3 out there that's all on that line.
we don't know that. Actually, those aren't all, like the positions are all in a line, but we don't know the directions of these two forces. And actually, those, well, in this case, I think they came out to be zeros, but like in general, they wouldn't all be in a line. So yeah, this one is not a two-force member. The two-force members, notice we never even isolated. They only came into it based on the tensions that they apply to the pins. Okay, so
F2, F3.
ah. F2 and F3. Okay, so what was the big benefit we got on this one? 2, 4, 6, 8, 10, 12. Well, that wasn't so great. And the number of equations matches, so you can solve this. So you get 3 equations for 1, 3 equations for 4, so we're at 6. Now these are all particles, so 8, 10, 12. So you have a system of 12 and 12, but we didn't get any benefit for this problem from doing that simplification. Sometimes you do, this one you don't. But that's how it works. So now I want to do one, I want to do this for a truss. So every member in a truss is a two-force member. And you'll see how this works, and it cuts down the number of variables. I want to, before I go on, let me point out that you never have to do a problem like this. And I would recommend actually that if structures totally make sense, everything's clicking, and you're just interested in sort of looking at the problem in a new way, this is kind of a cool extra challenge or whatever. But definitely don't think of this approach as something that's going to, like, if you're having trouble with structures, that this is going to make it simpler. It really is a more complicated way to think about it. But you do get a little bit of an number of equation benefit for doing it in a lot of problems. Okay, so let's do it in a truss. Okay, so we did this example. This was one of the first structures we did. We have an equilateral triangle. Uh, 500 Newton force applied to the pin at the top. All these angles are 60 degrees. And all these lengths are 1 meter. We did this with the full approach. And we got 6 equations for 6 variables. And the result that it gave us was that this member was in tension with a magnitude of 500 newtons. And this member was in compression with a magnitude of 500. So now we're going to do the same thing with the two-force body simplification. Okay, both of the members in this structure are two-force bodies, so we're not going to, that means we're not going to isolate any members. All we're going to do is isolate pins. Okay? So I'll number it like this. I'll call this 1 and this 2. And this is A, B, and C. And so let's isolate let's isolate the pin at B. So what forces are acting at B, at that pin at B? Yep, F1 is a tension going towards A, F2 is towards C, and then we have that 500 Newton force. So let's go to Newton's second law. What's a unit vector representing this force F1? Well, yeah, this is 30 degrees, so it's going to be, what, 240 degrees. So it's going to be F1 times negative 0.5, negative 0.866. F2 is multiplied by the unit vector positive 0.5, negative 0.866. Then we have this force vector 500, 0, and that's equal to zeros. And so we get two equations. The first one says negative 0.5 F1 plus 0.5 F2 is equal to negative 500. And the second one says negative 0.866 F1 is equal to positive 0.866 F2. The second one just says that F1 is equal to negative F2. So you end up with let's see. So if you substitute that in, you get that F1 is equal to positive 500 and F2 is equal to negative 500. And so free body diagram of member 1 looks like this, and a free body diagram of member 2 looks like this. Okay, so we got the same answer as that 6 equation system, this time with 2 equations and 2 variables. And so for the right problem, it can simplify the math a lot. But the downside is you have to treat every problem differently. It works, it helps a lot for some problems, not for others. You can't always use this simplification at all, because remember, any member where weight is included can't be a 2-force member. So anyways, that's what the truss simplification is based on. Any questions about that? So I just thought I should do that. You should see it. There's a good chance that at some point in some class, a professor is going to do a calculation that way. But you can do those calculations using that full method just fine. And yeah. What? I bet it never gives more equations. Usually it gives less if you can use it. That's been my experience. But I think, okay, like when the techniques that static books are based on were developed, there wasn't easy access to computers and calculators that did matrix calculations and that kind of stuff. So cutting down the number of equations, the number of variables was a big deal. And if a company needed to do a calculation to figure out what the loads were going to be and all the members of some huge truss that's used for a bridge, somebody had to do these calculations by hand. And so an approach like this was a big deal. Now, I mean, you can just Google truss calculator, and there are places online where you can just put in all the the coordinates of the different points, and it'll do the calculation for the truss. Calculators in MATLAB do big systems of equations, no problem. And so I think, to me, now there's not really much benefit to understanding the little subtleties that you need to cut down the number of equations a little bit. So. Any other questions? All right. Well, let's take a break, and I'll start with the next topic when we come back. So I'll start just a little before 2. All right. Anybody have any questions about that last stuff? Nobody liked that, I could tell. Doing that example and getting the same number of equations, that was disheartening, wasn't it? It was for me. Okay, so the next topic is internal loads and beams. And this is kind of the first topic into a big area of mechanics. Start of a major topic in mechanics. Which is basically, will it break and where will the fracture start? And I might have already drawn this picture up, but I'm going to do it again because I think it's a good demonstration of what we're talking about here. So, and because I like drawing hands. Okay, so here's your hands. Did I do this before at the beginning? Oh. Okay. Those are, oh, something's wrong with that thumb. Okay, so this person is holding a stick, bending it. Everything that we've been talking about so far has been calculating external loads on objects. And if you look at a free body diagram of this stick, it would look something like this. You'd have forces like this, and forces like this. But you know from experience that, so this free body diagram, you know, it shows the external loads. But that's not very helpful in telling you where this thing is going to start to break. You know from experience that the break is going to happen somewhere between the two thumbs, right? So what's going on there? There's no external loads acting at the place where that break is going to happen. So here's the break. Why does the fracture occur away from the external loads? At a place with no external loads. And the answer is, just because there's no external loads doesn't mean that there's no important loads happening to this material. the fracture happens at a place where there are big internal loads happening. So where you get large internal loads. And that means places where one piece of material is applying large loads to the adjacent material. Okay, so that's what we're trying to figure out. Where is one piece of the inside of this stick applying big loads to the surrounding pieces of the stick? And when we find that point, that's the point where this is going to break. Okay? So I'm going to start with sort of a simple example, and we'll just kind of think our way through it, and then we'll get into a systematic approach. So let's say that we have a stick, a beam, and there's 1,000 newtons applied at the center and 500 newtons applied at the two ends. If you put these loads into Newton's second law and the moment equation, you would see that this was an equilibrium. And we want to figure out what the internal loads are at this line. Let me give this a length. So let's say the whole thing is a meter. The 1,000's at the midpoint, and let's say we want to calculate the internal loads a quarter of the way across. And I'm going to break this up into piece 1 and piece 2. And the question is, what are the loads applied to piece 1 by piece 2? At that dotted line. Well, Newton's second law and the rotational equation don't tell us anything about loads that are happening inside our isolated body, right? You just have you draw your free body diagram, you apply the weight force, and then you just go around the boundary looking for forces. So it can never tell us anything about the loads happening inside our boundary. So we need to choose a boundary so that these, what we're calling internal loads, are external to our chosen body. So the free body I'm going to choose is this left piece, what I'm calling 1, where that dotted line is a boundary. Okay. Any questions about that? Free body diagram of piece 1. So think of it like this. If this is the whole body, there's the 500, there's the 1,000. Our free body is just going to be this. And we have to think about what loads are acting on this isolated piece. Definitely the 500 is acting. That one's pretty simple to understand. So where along this boundary is there contact now with the outside world? Yeah, on the right side, there's contact between the part that we've isolated and the rest of the beam. And you can think of that as a joint. What kind of joint is that? It's a fixed joint. Thanks. And so the loads applied to our isolated piece are just what you would expect with a fixed joint. So we have a force vector, I'll call that R, and we have a couple, MR. And those represent the internal loads. Those are the loads applied to our chosen part by the part that we left out. So Newton's second law says 0, negative 500 plus Rx, Ry is equal to 0. So R is equal to 0, positive 500. And then the moment equation, I'll do that about the about point. I'll put at the left end. So there's no moment produced by the 500. There's the couple MR. And then this distance, remember, was 0.25. So we get a moment that's equal to 0.25 times Ry. And if you have a positive Ry, would that make this rotate clockwise or counterclockwise around the about point? Counter. So this is positive. And so you get MR is equal to negative 125. Any questions about that? So that, in some way, that characterizes how strong the forces, the loads are that are applied to one side of the dotted line by the stuff on the other side of the dotted line. It tells you something about how likely this thing is to fracture at the dotted line. So now, does this represent the loads at the dotted line? Well, in some ways it does, kinda, but what if we had just arbitrarily chosen to isolate the other part, you know? So what if we'd isolated, so here's the body again. That's 500, 1,000. Actually, this one's gonna... Okay, so say that we had isolated this part instead. That seems like a reasonable way to do it, you know. Then we'd have this 1,000 Newton force here. We'd have a 500 here. We'd have our force R and our couple MR there. What would we get in this case for R and MR? Yeah, exactly. It's a Newton third law thing. So you'd get, this would give you that R is equal to 0, negative 500. And MR is equal to positive 125 Newton meters. And so it kind of tells us something about that line. The magnitudes are the same. But we'd like these values to be independent of which side we choose to isolate. So we'd like it to be independent of which side of the dotted line we isolate. And to fix that problem, I'm going to introduce this new sign convention that's sort of arbitrary, and it kind of obscures the fact that all you're doing is treating this cut as a fixed joint. But it does fix that problem of different answers working from the two different directions. So to fix this problem, we'll use a new sign convention. And what we're going to do is imagine that dotted line as a thin sliver of material, or a thin strip of material. Okay, so here's the body. And here's the dotted line. And we're going to imagine that what we're really doing is figuring out the external loads on this little strip, this infinitesimally thin strip around that dotted line. And the sign convention looks like this. So looking at that strip, a positive value of the horizontal component of the force, we're going to call that variable T. And if you're looking at the external load on, like if you're looking at this load on a face that's facing your left, a positive value points to the left, and to your right, it points to the right. Okay. The vertical, this one is sort of the opposite of what you would expect, but a positive value is that way, going down on the right and going up on the left, and we call this variable V. And then the bending moment positive is counterclockwise on the right, clockwise on the left. Where T is called the tension, V is called the shear force, and M is called the bending moment. Okay, any questions about any of that so far? So we have this kind of, it's a pretty arbitrary, I don't know how these decisions were made about what you call positive and what you call negative, but the key thing is we have it set up so that if you're working in one direction, a positive value means one direction. If you're working the other direction, it switches. So you don't have that Newton's third law thing happening. If we had isolated the right side, we would have gotten the same values as we get working from the left. So let me just do this problem again using this new sign convention.
Are we going to be using both sides?
We're just going to work from the left, but I'm just, the reason I'm talking about this is just to point out why we have we're introducing these new variables with funny directions, when it seems like it would just make more sense to talk about a force vector and a couple, you know. Okay, so same example again. But now with this new sign convention. Okay, so we have 500 acting down. The other ones aren't, this 1,000 and the other 500 down aren't acting on our chosen body. And then the only other loads we have are the loads from the fixed joint, which is T that way, V that way, and M that way.
That's the left side, so wouldn't it be the other way?
It has to do with which direction the face is, which face you're working on. You know what I mean? So
if you're on the left side of your separation line, all the new ones are going to be pointing.
So-
If you're on the right side.
yeah, so if so we're isolating the beam like this, you know, and so we use this T.
Okay.
Any other questions about that? Okay.
How did you come up with that arrow of V going down?
Because we are acting on a face that's, so think of an arrow pointing out of the face. The arrow pointing out of this face is pointing to the right, and so we use this direction for V. If we were looking at a face where the arrow pointed to the left, we'd use the V going up. Yep. And after I'm done with this, we can do it the other way too. I don't know, I sort of go back and forth on, like, I think people eventually after about the fourth time get tired of doing the same example over again, but sometimes it can be really helpful, I think. All right, so Newton's second law, we got 0, negative 500, plus, so now, this is something that is probably going to be confusing at times. Like, it'll make sense and then stop making sense and then make sense again and whatever. But think of T and V as scalars times a unit vector. Okay? So what you're trying to do is think of the unit vector that points in the direction of this arrow and this arrow. So for T, what's the unit vector that points in the direction of that arrow? Yeah, positive 1, 0. And T times positive 1, 0. Well, I'm going to write it like that first. So T times positive 1, 0. And then what's a unit vector in the direction of that V arrow? Yep, so we have V times 0, negative 1. And that's equal to the 0 vector. And you can write this as 0, negative 500, plus T0, plus 0, negative V, is equal to zeros. Okay, so T is equal to 0. V is equal to negative 500. And now we'll go to the moment equation. The about point is going to be at the left end point. So what's the moment produced by the 500? 0. What's the moment produced by t?
0.
0, because the line of action goes through the about point. What's the moment produced? Well, the easy one is m. You just add that on. Now, what's the moment produced by v?
0.25.
Yeah, the moment arm is 0.25. The force is v. And if v is positive, does that make this rotate clockwise or counterclockwise around the left endpoint? Clockwise, so this is negative. Like if v was equal to 10, you'd have 0.25 times 10, and it would cause this thing to rotate this way around that point. Like at this point with the hinge. Okay, so we know the v value, so we can plug this v value in for v in this equation, and you get that m is equal to negative 125 Newton meters. Okay, let's do it again. Okay, so we'll do it. This time we'll go from the right, and we'll see that Newton's third law thing doesn't come up. Again, from the right. Okay, so they're the external loads. And now the face, where we're trying to calculate these internal loads, is pointing towards the left. So what direction would a positive tension be? Yeah, to the left. And what direction would a positive shear force be? Up. And positive bending moment? Clockwise, yeah. Okay, so Newton's second law says, what's a unit vector in the direction of t? Yeah, so that's t times negative 1, 0. The unit vector in the direction of that v? Yep, so v times 0, 1. And then we have 0, 1,000. And 0, negative 500 is equal to zeros. And so you get t is equal to 0 again. V is equal to negative 500. And the moment equation, let's do that calculation around the right endpoint. So the 500 doesn't produce any moment. The 1,000, there's a moment arm of 0.5. And if this is the about point, would that 1,000 Newton force make it rotate clockwise or counterclockwise? Yep, clockwise, so we have negative 500. If you have a positive value of m, is that a positive couple or a negative couple? It's a clockwise, it's drawn as a clockwise thing, so
Negative.
that's going to be negative. So negative m. And then the last thing is the moment produced by that shear force. What's the moment arm? Yeah, 0.75 times the force v, and then would that cause a clockwise or counterclockwise rotation about that point? Clockwise, so this is negative.
So what's positive about it then? When we drew it, you said that was positive.
Yeah.
But it's negative value. What's positive about it?
Yeah, so again, it's a unit vector thing, but it's not like as obvious with the moments because in 2 dimensions we usually think of those just as scalars. But what it really is you have this value m times a unit vector of 0, 0, negative 1. And so if m is positive, like if you had 50 for this, you'd get a negative z component of your moment.
So that's just depicting the scalar.
Yes, it's just depicting this equation shows m as the z component. Like this equation is just the z component equation of the moments.
As it would be in any 2D, but not 3D.
Right.
So when you go to 3D, it's different.
Well, in 3D it's not as, since you're doing everything as vectors anyways, because in 3D the moments are all vectors. You have non-zero components everywhere, so you have to represent it as a vector. And so it's not as weird to think about unit vectors and stuff in 3D as it is with 2D.
So it's only positive to make it negative in the end because it's clockwise.
Right.
Okay.
Yeah. Okay, so if we plug these values in, we get m is equal to negative 500 plus 375, which is negative 125. Is that what we got before? Good. We got positive before?
No, we had negative.
Just when we did it from the left with the new sign convention, we got negative. Okay, so that new sign convention eliminated that Newton's third law issue. But now you have to remember this sort of arbitrary sign convention. Yep.
Where do we get the negative 500?
That was from the 1,000 Newton force acting up with a moment arm of 0.5.
How come I see you've been doing this the whole time, but why isn't the M have a moment on?
Because it's just a couple, so it's just a pure moment. Just like when you do fill out that pancake table, you don't worry about the row vector or anything. And just like I was saying when we were doing distributed loads, if you want to, maybe at the beginning, while you're getting comfortable with it, if you want to fill out the table, that works fine here. For these, since the beams are always horizontal, I start going to this sort of shorthand approach, but the table works fine here. And as far as remembering the sign convention, for the tension and the shear force, I can't help you, but for the bending moment, I can help you never forget. This is positive. And this is negative. Okay, so that's like, so if you applied positive bending moments, it would bend it like a smile. If you applied negative bending moments, it would bend it like a frown. But the other two, there's not really any like rhyme or reason. Any questions about that? Yep. Yeah, the sign conventions. So if you're on we're always going to go from the left. So basically you can just remember this and this and this. But this is the sign convention. So if you are working from the right, which you can do, we're just not going to do, you just switch the signs, switch the directions. Any other questions? Okay, so this approach, this would work, what I just did here would work if you had a candidate in mind that you thought, like, I'm afraid this beam's going to fracture here. I want to calculate the internal loads at this point. But more often, you want to look at the internal loads all the way along the beam and see where it's a maximum or a minimum or whatever. So the next step is calculate the internal loads for all points along the beam. Not just one, and there's uncountably, infinitely many points, so we need a better strategy than just starting a list. So what we want to come up with is we want to represent the location along the beam as an x value, and then represent these things as functions of x. So we want to let x represent a point on the beam, and calculate t of x, v of x, and m of x. Okay, so let me do an example to sort of show the idea of how this is going to work. So let's let x represent any number between 0 and 0.5. And let's try to calculate the internal loads. Okay, so we're going to isolate a piece that goes all the way from the left to some arbitrary value x on the right. So this point here is x. And no matter what this x value is, it could be 0.01, or it could be 0.49, right? Or it could be anything in between. But in any case, in any of those cases, we're still going to be having this, since we're isolating a piece that goes all the way from the left, we're still going to have that 500 Newton force acting down. And in any case, we're still going to have the tension, shear force, and bending moment acting on the right side. Okay, so that's the free body diagram, no matter what that x value is.
They're not going with the 0.25.
Yeah, right. We're not. This x is what 0.25 used to be.
So it could go all the way up to 1,000. Why did you say between 0 and 1,000?
Well, the reason that that I didn't let it go farther than 0.5 is this would not be an accurate free body diagram anymore if we went past 0.5, because we'd be missing that 1,000 Newton force. Okay, and if I put that 1,000 Newton force in to make it accurate for things between 0.5 and 1, then it wouldn't be accurate anymore when I looked for x values less than 0.5, because here we don't have that 1,000. So there's an important cutoff that happens where that point force is. Okay, and that's going to be like a big issue with this. Okay, so Newton's second law says 0, negative 500 plus T0 plus 0, negative V is equal to zeros. And so that says that no matter what x value we're at, T is equal to 0, and V is equal to negative 500. And the moment equation with the about point at the left end says M. So there's no moment produced by the 500. There's no moment produced by the tension. There's M, and then there's a moment produced by V. And now what's the moment arm? That's right. And is it positive or negative?
Or no, it'd be negative.
Negative. So this time, instead of having a moment arm of 0.25, since this is an arbitrary length with a length of x, the moment is minus Vx. And that's equal to 0. And so M is equal to Vx, and V is negative 500, so M is equal to negative 500x. So now T, V, and M are functions that give the internal loads for any x value between 0 and 0.5. Okay, so that means that if we plug 0.25 in for x, we should get what we got in the first example. These two, there's no dependence on x, so those work. And if you plug in 0.25 for x here, you get m is equal to negative 125, and that's what we got before.
The endpoints are not included, right?
0 and 0.5 are not included, that's right.
Will there ever be brackets? Will there ever be included?
Nope, nope. Any other questions? Okay, so that's an introduction to this, and so next time, tomorrow, we'll talk about how to choose the endpoints, more details. All right.